Shen from Esty, who's going to be telling us about how they do A/B testing.
Yeah. So hi everyone, my name's Kelly. I'm a software engineer on the analytics engineering team at Esty, and I mainly work on improving our experimentation platform. Today I will be talking about how we handle a common problem in A/B testing, peaking our data early. Now, the analytics team at Esty mainly uses R and Python currently, but I have very positive experience using Julia in college, so I use Julia for part of the project. And first, let me give you a short introduction to Esty and A/B testing. Esty is an online marketplace for handmade, craft, and vintage goods. We don't own any inventories ourselves, but we connect sellers and buyers from around the world to each other. And our items range widely, from the $10 turtle earring that I'm wearing today to a $50,000 engagement ring. And for each item, Esty gets 5% listing fee. The rest goes to our sellers. Here are some more numbers. We have 2 million active sellers, 34.7 million active buyers. Last year, we had 3.25 billion annual GMS, which stands for gross merchandise sales. GMS is one of our key metrics. So for the $50,000 engagement ring, if it gets sold, that's $50,000 GMS for us. And as of end of March, we had 50 million items for sale. What is A/B testing? A/B testing is where a company wants to assess if a change of feature or algorithm is effective or not. When a user goes on our site, they can be bucketed into either one or multiple experiments, depending on the mutual exclusivity of the experiments. And once they are bucketed into an experiment, they can be in either the control or variant group, and there can be more than one variant. For example, if we want to test the effectiveness of a button color change from black to orange, then a user who goes on our site will see either of those two button colors. And A/B testing really is everywhere, from big tech companies to small non-tech organizations. And companies like Google, Facebook, LinkedIn, they have published papers on their experimentation platforms and the challenges that they faced. And in A/B testing, we're really looking to determine if the metric we care about, for example, the percentage of visitors who click and end up buying, is different between the control and the new experience. And to do so, we can look at the p-value, which indicates the frequency that we will see a difference as big or bigger than the one between A and B when there's no underlying difference. And when the significance level is low enough, for example, 5% is industry standard, we declare that our result is statistically significant and we can end the experiment. So you might think that we can just collect some samples, calculate the p-value, and if the metric we care about has a p-value below 0.05, we can say that the metric is significant. But no, that's exactly what peaking is. Because for the p-value to be accurate, we have to have fixed the sample size in advance and only look at the p-value once. Checking the p-value early and stopping an experiment early would increase the rate of false positives, because you would think that there's a difference between A and B when there is not. And in addition, the more we peak, the higher the false positive rate would be. And let's look at an example. For example, suppose we run an experiment where the conversion rate is 50% for control, and we accept 10% false positive rate. If there is no peaking, so in other words, the sample size is fixed, then and we consider we consider the case that B converts at 50% as well. Then the false positive rate would be about 10%, like this graph shows. However, if we peak at every observation, then after 500 observations, there is a greater than 50% chance that we will incorrectly stating that A and B are different, which is 5 times more than the expected. Now, peaking 500 times is a little extreme, but it tells the point. And you might think that the simplest way to solve the problem would be to just fix the sample size in advance and run the experiment until the end. but it's just not practical for a fast-moving company like Esty because first, the opportunity cost for longer experiment is pretty considerate, and we would love to conclude an experiment at the earliest to leave space for other experiments. And secondly, sometimes we are just not sure the effect size that our user wants in advance, and our users are the many product teams at Esty. So, and we want to provide our users with accurate interpretation of their data as soon as possible. So we tackle the problem from two sides. One is the platform, and the other is really trying to prevent users from peaking behaviors. In terms of platform, we transitioned from the traditional fixed horizon testing to sequential testing. So sequential testing computes the probabilities of false positives at every step of the experiment using dynamic programming. So since we can compute those probabilities, we can adjust the test false positive rate at each step. And then we can keep the total false positive rate below a set threshold. We consider multiple sequential testing approaches, and I will be talking about two in a minute. We did the investigation work by looking at our historical experiments. We have multiple years of historical experiments, as well as simulating some different scenarios. And most of the simulation work was done in R, but I did some analysis in Julia, for example, the trade-off between power and significance, and the effects on length of experiments, and the effect on experiments with different conversion rate. And I want to briefly define conversion rate. So conversion rate is the number of conversions divided by total number of visits. So if Esty gets 10,000 visits and had 1,000 sales, that's 10% conversion rate for us. And baseline conversion rate is the current conversion rate for the page that we're testing. So it's a powerful metric for us to measure the performance of our website and app. And the first method we considered was Pocock Method. It compares the z-score to an alpha spending curve and stop an experiment when the z-score is greater than alpha. And it considers baseline conversion rate, which is great, unlike some other methods that we would have to use different methods for different conversion rates. And it also can be set up to not need equal data sample size. However, it does work better if we have equal number of samples within each test intervals. In addition, it's not able to detect small changes quickly, which is a huge drawback for us. And another method that I want to talk about is sequential testing with difference in converting visits. And we will look at the raw difference in converting visits and stop an experiment when this difference is large enough. And the result is a p-value threshold curve that changes dynamically. And in addition to this curve, we came up with a haircut equation to account for the cases when percent change is being overestimated. This method is great at detecting small changes quickly, which is very suitable for our use case. It does have some weakness. For example, it's not ideal for a metric with very high conversion rate because it does not take into account number of failures. But we did choose this method over Pocock because of the advantage it showed in detecting small changes quickly. And we also did some user interface changes to try to prevent our users from peeking at their data. And so in addition to p-value, in A/B testing, we also really care about power and confidence interval. Power is the probability that if there is an effect of a certain magnitude, we would correctly reject the false null hypothesis. So before, we did not include the actual power in the table, and we just show data expected in, which that parameter depends on power. And also, we really care about confidence interval, but before, we only just show an interval. But after we made the UI changes, we decided to include some messages in both the table and the popover table headers and also to include the actual p-value and as well as a confidence interval visual to indicate the size and position of the confidence interval, because that's what we really care about in confidence interval. Lastly, I don't really have time to go into this, but we did also consider some other issues. First, there is a trade-off between power and confidence, power and significance, because between false positive and false negatives, if we decrease the probability of one of them, the other increases. And also, we have experiments that have other than 2 treatments. For example, AA experiments and multivariate experiments. So we had to do some extra setup for those experiments. And lastly, at Esty, we have a lot more data on weekday compared to on the weekends. There is actually an R package called GroupSeq that deals with the case, and we can easily use rcall in Julia to use it, or maybe I can write it in Julia. And that's it. Thank you so much for listening, and I want to give a shout out to the analytics and data engineering team at Esty. Thank you.